hardware bridges the gap between our messy physical world and the ultra-precise digital world of computers. I mean, we interact with these machines constantly, right? But how does a physical button press or the actual sound of your voice get inside the computer? Well, that's exactly what we're going to figure out today.
We've got 6 main topics lined up for this explainer, basically acting as case studies for how real-world data gets captured. We'll be hitting barcodes and QR codes, digital cameras, keyboards and the optical mouse, microphones, 2D and 3D scanners, and finally, touchscreens. Let's get right into it.
Okay, so let's set the stage by defining our core concept here. An input device is, simply put, a translator. It's any hardware component that lets you enter data or control signals into a computer. Text, images, sound. These devices take our human actions and translate them into the binary language of ones and zeros. Because at the end of the day, that is the absolute only format a computer can actually process and understand.
Section 1. Barcode and QR code. Scanning data directly. We're starting with a technology you literally see every single day, whether you're at the supermarket checkout or checking out a book at the library.
Let's break down what's actually happening when you scan something. A traditional barcode is just a series of dark and light parallel lines. When you scan it, a red laser or LED shines onto that code. And here is the really clever part. The dark bars absorb the light, while the white spaces reflect it back. A sensor catches that specific pattern of reflections. Then, that varying analog reflection gets converted into a digital signal. The store's database reads it, pulls up the price, and updates the inventory instantly.
Now look at how this tech has evolved. We started with those 1D barcodes, which are great, but they only hold about 30 digits and need special laser scanners. Enter the QR or quick response code. Instead of 1D lines, it uses a 2D matrix of light and dark squares called pixels. Since it works in 2 dimensions, it can hold up to 7,089 digits. That massive jump in capacity means a QR code can store entire website addresses, and it can be read in a split second by the camera right on your smartphone.
But there's a catch. While QR codes are super convenient, they also introduce some real cybersecurity risks. Because literally anyone can generate one. Hackers do this thing called ad tagging, where they hide malicious code inside those innocent-looking squares. If you scan a tampered code, it might secretly redirect you to a fake website, download a virus, or even give a hacker unauthorized access to your phone. So definitely be careful what you scan out there.
Section 2. Digital cameras. Capturing light as binary data. Next up, let's look at how we capture our memories digitally. The way light flows through a camera is actually mind-blowing. When you snap a picture, light travels through the lens and strikes a light-sensitive plate made of millions of tiny sensors called photodiodes. Usually these are CCD or CMOS sensors. Each individual sensor acts as a single pixel. It detects the intensity of the light hitting it and instantly converts that light into a continuous electrical charge.
But remember, our golden rule, computers only speak binary. That continuous electrical charge is an analog signal, so we absolutely have to use an analog to digital converter, or an ADC. The ADC takes that continuous charge and slices it up into specific, discrete digital values. For instance, if your camera has an 8-bit ADC, it assigns one of exactly 256 brightness levels to every single pixel. And just like that, a beautiful sunset is transformed into a massive grid of ones and zeros.
Section 3. Keyboards and optical mouse. Standard computer control. Let's transition over to the classic peripherals we use pretty much every single day.
You might not think about it, but right under the keys of your keyboard is a complex membrane. When you press a key, let's say the letter H, you are physically pushing a switch down and completing a tiny electrical circuit. The CPU detects exactly where that circuit was closed, and then it looks up that key's unique ASCII binary value. That's how it knows exactly which character to throw up on your screen.
And right next to that keyboard is usually your optical mouse. These completely wiped out those old mechanical mice that had the rolling rubber trackballs that would always get clogged with dirt. Instead, an optical mouse uses a red LED to light up your desk, and a tiny CMOS sensor acts like a microscopic eye, snapping thousands of pictures of the surface every single second. A processor then compares those rapid-fire images to figure out exactly how fast and in what direction your hand is moving. No moving parts, super reliable, and hey, you don't even need a special mouse mat anymore.
Section 4. Microphones. Turning sound waves into electricity. Moving on to audio. Let's see how we capture the physical waves of our voices. Okay, this is pure physics at work, and it's so cool. When you speak, Your voice creates invisible vibrations in the air. These sound waves hit a super thin membrane inside the microphone called a diaphragm, causing it to vibrate. Attached to that diaphragm is a little coil of wire, suspended right inside a permanent magnet. As that coil moves back and forth inside the magnetic field, it actually induces a raw electrical current that perfectly matches the pattern of your voice. After that, our trusty analog-to-digital converter steps in and turns that current into digital audio.
Section 5. 2D and 3D scanners. Digitizing physical objects. Let's talk about getting physical documents and real-world 3D objects into the computer.
To make sense of this, let's compare the two technologies. A 2D scanner maps a flat XY plane. It uses a bright xenon lamp and mirrors to reflect a document's image onto CCD sensors, digitizing it pixel by pixel. A 3D scanner, on the other hand, captures solid objects. It maps the X, Y, and Z axes using lasers, magnetic resonance, or X-rays. Think of a medical CT scanner. It takes hundreds of 2D slices to build an incredibly detailed 3D digital model of the human body.
Now, a brilliant application of 2D scanning is OCR, or Optical Character Recognition. OCR software doesn't just scan an image, it actually reads the letters, turning them into editable, searchable digital text. You've probably seen this in action at airport security. The e-gates use a 2D scanner combined with OCR to instantly read the printed text on your passport and verify your identity.
Section 6. Touchscreens. Interactive display technology. For our final topic, let's look at the tech we literally carry in our pockets. There are three main types of touchscreens we need to cover.
First up is the capacitive touchscreen. This one takes advantage of a biological fact. Human skin naturally conducts electricity. The screen itself projects a tiny, invisible 3D electrostatic field. So when your bare finger touches the glass, your body literally steals a tiny bit of that electrical charge, causing a disturbance in the field. Sensors in the corners instantly detect that voltage drop and calculate exactly where you tapped.
Next, we have the infrared touchscreen. For this one, imagine a microscopic, invisible grid of laser beams crisscrossing right above the glass. The edges of the screen are lined with infrared transmitters and sensors. When you touch it, your finger physically breaks those intersecting beams of light. The screen's microcontroller simply calculates the exact X and Y coordinates where the light was blocked to register your touch.
The third major type is the resistive touchscreen. Now this one is entirely mechanical. It's made of a flexible top plastic layer and a bottom glass layer with a microscopic gap of air between them. Both layers have an electrically resistive coating. When you press on the screen, that physical pressure bends the top layer down until it squishes against the bottom layer. That physical contact completes an electrical circuit, and the system calculates your touch location based on the voltage change.
So why have different types? Well, look at their real-world uses. Capacitive screens, like the one on your smartphone, give you brilliant visual clarity and let you use multi-touch gestures like pinching and zooming. But try using them with regular winter gloves, and nothing happens, right? Resistive screens, on the other hand, need actual physical pressure. They don't do multi-touch and aren't quite as clear, but they are highly durable, water-resistant, and work perfectly even if you're wearing heavy work gloves. That makes them absolutely ideal for industrial or outdoor settings.
We've covered everything from the barcode scanner at your local grocery store to the capacitive screen sitting right there in your pocket. Having seen how these incredible input devices translate our physical reality, whether it's our touch, our voice, or the light around us, into binary data, I want to leave you with this final thought. As technology continues its rapid advance, what human action or physical sense do you think we are going to digitize next? Thanks for joining me on this explainer, and keep exploring the amazing world of computer science.